I'm Alexis Willie, and today we're going to be talking about how to implement large volume injections using your MMI inlet to help achieve some low detection limits on your mass spec. So our MMI inlet and applications, again, why would you want to use what we call a multi-mode inlet? It has a lot of benefits, really. Being able to do cool split or splitless injections for your sample. And again, why might you want to do this? If you have a sample that is thermally labile and tends to break down into a hot inlet, being able to inject into a cool zone really has a lot of benefits of helping prevent sample breakdown. Another application is doing large volume injections. Typically into the GC when doing liquid injections, you might only be injecting 1 to 3 microliters. However, there are times when it may benefit for doing a larger range, say into the range of 10 to 100 microliters. If that's the case, your MMI inlet operates in a mode called solvent vent mode, where we're able to sweep that solvent off and hopefully preserve only the compounds of interest into the inlet and then onto your column then. So large volume injections, again, when a customer want to use these? So customers doing low-level analysis in the environmental world, pesticides, forensics, drugs of abuse, being able to look at your GCMS in SIM mode, or if you're operating on a triple quad, being able to look at very extreme low levels on MRM mode. Again, samples that tend to decompose very quickly. A large volume injection will help you get more onto column then. And like I've stated before, whenever lower detection limits are needed. So next, something we come across in the chromatographic world tend to be bonus peaks or ghost peaks. So a peak in your chromatogram that you are not expecting and doesn't really look like your traditional Gaussian peak for your compounds. Again, where might these bonus peaks or ghost peaks come from? So contamination from your injector or your flow, contaminated consumables, carryover from backflash or of a previous sample. And this is the one we're going to focus on here. Could also come from bad tanks of gas or traps that have expired. Septum bleed. So again, being able to change out your consumables frequently. And again, it's good to note that if you run an actual black sample through your system, whether it's a solvent blank or just a system blank, no injection at all, in theory, it should be blank. If it's not, again, you have contamination or what we're going to talk about, this backflash coming from somewhere within your inlet. Here is a typical chromatogram right here, and this one is showing, unfortunately, a bonus peak. So you see we have our nice Gaussian peaks, all straightforward, sharp as can be. And then right here in the middle, we have this kind of ugly triangular peak that has a huge fronting on the beginning side of it. And again, this is not a real peak of interest. This is something that is coming from somewhere inside your system, from contamination or so forth. Ghost peaks, where do they come from? So what can tend to happen in any type of GC inlet is you can have an overloaded injection. So you've injected too much liquid into most likely a hot inlet. And as soon as it hits that hot inlet, it vaporizes, and the vaporization kind of goes everywhere. The liner volume can no longer contain it. It has exceeded the liner volume. And so we get this backflash of contamination that lives in the septum purge line, your carrier gas line, the split vent line. And again, once it's in there, into these cooler spots, it's stuck there and really is hard to get out. So we have to make sure that we're taking our due diligence when we're doing any GC injection, that we are keeping the contents of our sample, of our injection, into the liner volume itself. And I know a lot of questions we always get is, well, how do I know? How do I know if I'm creating this backflash with any of my GC injections that I'm doing? For that, we have what we like to call our GC calculators. This is a free set of software, does not require any licensing. You can download it directly from Agilent's website here. The link is below that you can type down. If you have any of our Agilent software that are controlling your current GC systems, it actually lives within the software. On the GC edit page, it's the very last tab. Or again, like I said, it can be a standalone feature as well from our website. And you get this little desktop icon. And from in there, when you click on it, it opens up to 4 different options. The top one being the vapor volume calculator. This is the calculator that you shall use to see if you are actually creating any backflash within your method. And I find it extremely useful when doing any method development work. Here we have the GC calculator set up showing water is a solvent. And with that, using a liner, a single tapered liner that currently has a volume of 850 microliters. So with a 1 microliter injection in our hot inlet set at 250 degrees and our inlet pressure is set at 15 psi, you can see we are well exceeding the liner volume for the vaporization of water here, well over 100%. Ideally, it's nice to have that number somewhere between, say, 25% and 70% of the liner volume is where you would like to live. But obviously, we do not want it in the red over the 100% mark. So again, how do we change this? How do we get our vapor volume back into the contents of what our liner can hold? We have a few options. We can reduce injection volume. And again, you might be saying, well, I don't have that option. That is not built into my method. You could try a lower inlet temperature. And again, maybe that doesn't work for you as well. You consider changing your liner itself to create a larger volume within the liner. But again, you can only go so high with the liner volume. Other options are pressure pulsed injections in either split or splitless modes. Could also consider changing your solvent. Again, maybe you don't have to inject water and you could move to something else that doesn't have as much vaporization on expansion. Or lastly, you can consider using solvent vent mode with an MMI inlet. So being able to sweep away your solvent and leave only your compounds of interest behind. That way you're not exceeding the liner volume. So in this scenario here, it's showing a simple fix where we took the injection volume and just cut it down in half from 1 microliter down to a half a microliter. And as you can see, our vapor volume calculator is now happier and well within the green range. The vaporization has, again, been cut in half due to the half size of the injection volume. And again, here we have a scenario where we have to do a larger injection. So for this, we are taking 3 microliters of dichloromethane into our hot inlet on the left-hand side here, using a splitless inlet at 260 degrees. And you can see at 3 microliter injection, we are, again, well exceeding our volume of vaporization that our liner allows in this scenario. But you can see just by moving over to a cold splitless injection on our MMI and utilizing it in that mode, we actually drop the vaporization back into an acceptable range. It's no longer in the red, back down into the yellow at 87%, just by lowering that temperature from 260 degrees down to 60 degrees. So that proves to be a nice option there. So then the other option we have is, again, moving over to solvent vent mode. So solvent vent is an option if you're in your GC edit parameters. Down on the bottom left-hand side there, you can choose from solvent vent. Again, your options are split, splitless, pulsed split, pulsed splitless, and then solvent vent if you're on the MMI inlet. As soon as you select the solvent vent option, the solvent vent wizard will automatically appear right below it. Because with solvent vent comes a lot of different method parameters that, in addition to what you're used to, that have to be set up. So using this wizard is a nice little technique to help you get the parameters hopefully set correctly. Some other parameters that you have, again, on your MMI here is being able to, again, cool down your inlet and then ramp the temperature up as needed. So up in the upper right-hand corner here, we have your temperature ramp. So again, this is specifically for the inlet itself, not the oven here. And we're able to start at the cool 60 degrees and hold it for a short period of time, and then ramp it extremely fast up to our final temperature of 325 to burn off anything that's left. Another thing important to note on here, and this you would see in most modes here on whether you're in splitless or on the MMI, is your septum purge. Actually has 2 different modes that people don't tend to know what both of them do. So you can see we're listed as standard right now. So septum purge flow mode is standard. Standard is meaning that whatever you have your septum purge set at, so ours is currently set at 3 mils, that 3 mils is always on, no matter what. At any point in the injection, at any point during your run, that 3 mils is always on. And again, it's sweeping just below your septum itself, taking away any contamination that has built up from there. You do have the option of changing that from standard over to switched. And what that means is, yes, your 3 mils will still almost always be on, but during the injection itself, if you're doing a splitless injection, it will turn off that 3 mils just for the injection portion itself. And then you've actually created yourself a true splitless injection. Because if that septum purge remains open throughout the injection process, you're losing just a tiny bit out of that septum purge line from your splitless injection. So this could be just that one extra thing that helps boost your sensitivity, just that extra little bit that you may be looking for there. All right, let's jump back into the Solvent Vent Wizard, like I stated before. Like I said, the box appears automatically when selected in Solvent Vent mode. Once you click on the box for the Solvent Vent Wizard, it opens up this extra software here that helps you create your solvent vent method for you. And again, there are tons of benefits to using a solvent vent injection procedure here. It allows sample prep of smaller volumes. Again, we're able to reach lower detection limits by putting more onto column. It reduces the thermally labile compounds and their breakdown. It's because it is a gentler introduction of the samples into your system here by being able to do it in a cooler mode and at lower pressures. And again, it comes with this little nifty software to help you set it up for you. So what you're going to do is you're going to tell it what solvent you're using, how many microliters you would like to inject, roughly about the boiling point of the first compound of interest. And then because we pulled this up through the software, it's already going to know our syringe size. So it's important to note that if you're trying to experiment here with what larger injections could look like, 10, 15, 20 microliters, it will not let you do so unless you actually have a larger syringe configured into your software. So you have to exit back out of this box, change it in your software into the configuration porches, and then come back into the software. And you should see it updated as to which syringe size you have. So once you click over and enter all the initial parameters in, it will create this screen right here. And from here, you have your solvent vent parameters that it has determined for you. And again, there's some judgment as to whether or not this works for your system or not. But we have the vent flow that it's given you. We have the vent pressure to use during that time. And then we also have the outlet pressure gauge. So this is currently set at 0 because we are flowing to a mass spec. So we're heading to a vacuum source here. But this can also be used for standard GC detectors as well when running solvent vent. And if that's the case, you would just put atmospheric in there as far as your PSI goes. Now you can see in this scenario here, it's saying that our inlet starting temperature should be -5. Well, now for the way our system is set up, that's not actually capable. While we have cryocooling on the system, I'm not using cryocooling on my system. I was actually using compressed air, so I'm not actually able to achieve anything that is subambient in my system here. So again, for me, that temperature does not work. So I stick with a standard 60 degree starting temperature, which my MMI on compressed air has no issue. However, if you have actual cryo cooling set up on your MMI and you're using either CO2 or liquid nitrogen, then you are able to reach these subambient temperatures without issue. So it's just important to note what type of cooling you have selected on your MMI and what your system is capable of, and just keeping it within the range of that. The other important information on this screen right here is the suggested vent time. So this one is currently reading 0.2 minutes. So it's saying, again, after 0.2 minutes, it will go ahead and open up and get rid of the flow and increase our pressure back up, and then actually go ahead and perform our splitless injection technique then after that. Here are all the solvent vent mode parameters listed out all in a straight line here. So that way you can see how the method, again, potentially how a method could be set up and how the parameters play into each other. So again, the initial is the top. So our starting temperature for our inlet. And again, we always like to recommend that it is about 30 degrees below the boiling point of our first peak here of interest. And the initial time, again, how long do you want to hold at that low temperature for your inlet before you start increasing it to the final temperature? So rate 1 is the increase rate on your MMI to the final temperature for your inlet, which this one is set at 250. So the pressure that is listed below that at 15 psi, that is your actual inlet pressure to achieve your column flow. This is the pressure that your inlet will be set at when not actually during the injection procedure itself for the solvent vent. Just below that is the vent pressure. So again, normally a lower pressure with the vent flow, so how much flow you want over it. And this is what is sweeping across that liner and taking your solvent out of the picture. So if you're doing a very large injection of say 10 to 15 microliters, it will sit there at that low pressure with all that flow running over it, sweeping away just your solvent and leaving your compounds of interest behind. And again, the vent end time is how long do you want that to occur for? And again, there is no magic number. The Solvent Wizard works great, but this is a number you might have to play around with to find out what works best for all your compounds. Then after that, we have the purge time and the purge flow. So once the vent has completed itself, it then moves into just a splitless injection. You want to make sure that purge time is greater than the vent time. If you have the purge time either be exactly the same or even less than the vent time, you're risking having your flows change too quickly and then your injection not really be set yet and actually still having remaining solvent left in your liner there. And again, the purge flow at the end is how much volume do you want to sweep through that inlet to evacuate whatever was remaining that did not make it into the column. And again, septum purge flow is the flow that's flowing just under your septa there, sweeping away any contaminants. And in this scenario here, we have septum purge mode set as standard. But again, the other option is having it set as switched to create a true splitless injection for yourself then. So now that we've gone through the procedures of setting up a solvent vent method using our MMI and inlet, and again, why you might want to do that, we're going to go ahead and look at an actual case study here. So this was using the MMI inlet and a very large volume injection to determine ultratrace level analysis on the GCM-SMS of organochlorine pesticides using the MMI inlet. Here we have listed out the actual method parameters that were used for this procedure. We used an 8890 GC with a 7010B mass spec with the HES source. We have a less than 18-minute method, and we were injecting between either 10 or 15 microliters and using our MMI inlet at 40 degrees in solvent vent mode. We started at the 40 degrees and held for 0.32 minutes and ramped it up at 600 degrees a minute all the way to 325. Our vent procedure was 150 mils at 2.5 psi for that 0.32 minutes. And then our purge was set to 60 mils. And again, the purge opened up at 2.52 minutes. And then we had the septum purge into switched mode, like I said, to help with sensitivity purposes. We were using the Agilent Ultra Inert bottom fritted liner, part number is there. And on this, we were running the 8270 UI column, 30 meter 2525. Helium is a carrier gas at roughly 1.25 mils a minute in constant flow. And we were retention time locked down to ASNAP-THENE D10. Oven was set to 40 degrees for that first 2.52 minutes, which is common procedure here when running splitless mode to hold the oven just as long as you're holding the purge time. And then from there, we ramped accordingly. Mass spec transfer line was set at 320. On the mass spec side of things, we had a 6-minute solvent delay since we did not have any early eluders. Our gain was set at 10 and we were operating in DMRM mode, so based on retention times for those MRMs. Our source was up at 300 degrees and our quads were at 150 with a total MRMs throughout the run of 65. And again, why did we use this technique specifically on these organochlorine prevent mode for these pesticides? Right here is a good example of why we chose solvent vent mode by talking about dieldrin and endrin. They are two known compounds that will break down into a hot inlet. So by doing a cooler inlet and by injecting a lot more onto column, we're actually able to obtain the sensitivity that we need from them. It is no surprise that, again, the dieldrin and endrin do not really provide very good ions for choosing when picking our MRMs. They don't have as much selectivity from the higher masses when they fragment apart from each other. This here is showing the dieldrin in the spectra from the NIST 20 library. And here we have endrin, where again, the same thing. The higher masses, there are really no good ions to choose from as far as selectivity goes, and ions that are specifically unique to these compounds. But by doing a larger volume injection, again, we're able to get more onto column to help with those detection limits. Another thing in this specific project was the cleaning mode technique that was done in between batches. So this is our jet clean option here, which was on the 7010B to help keep the ion source clean in between each run, since we were looking at such low detection limits, making sure there was no contamination or carryover on the source side of things. So by doing jet clean, we're actually just piping in a little bit of hydrogen while the system was offline and running that hydrogen because it's such a good scrubbing gas to help keep our source extra clean. And again, the benefits of using jet clean itself is helping reduce downtime. You have the options of running in an online mode or an offline mode. So online being when your actual samples are running. So are you. You have the hydrogen coming in as well, helping keep the source clean. Or again, offline mode like I did, by just running it whenever you need to in between runs to help ensure cleanliness of your source there. But by doing this, it can really help prevent overall downtime of your system, of having to take the system down to clean the ion source and then get it back up and running again. So again, this was just a little technique that was used in this project. Here is my chromatogram of the organochlorine pesticides. So this is a 50 ppb standard here of a 15 microliter injection. And you can see the nice sharp peak shape we are getting throughout the whole chromatogram here, even by injecting that much onto column. Okay, so here we have listed is the organochlorine pesticides, the calibration ranges and detection limits, and this is using the 15 microliter injection volume. So you can see we have the compounds listed as well as their low level limit and their high level limit. Most of the compounds being able to reach the 5 ppt mark as far as detection limits and calibrated up to 50 ppb, giving us a very nice linear range. We have the average RF listed, as well as what the R squareds are if calculated using linear, and if they were weighted 1/x, along with the relative standard error percent on the side. So overall, for the range and the extremely low detection limits that we are seeing, again, very good average RFs for all of them, and RSEs. This is the same data here, but with the 10 microliter injection. Again, we are still able to achieve, even on 10 microliter injections, 5 ppt for a lot of the compounds. Some of them are up to 10 ppt now, and so forth. And the linear range is still there. Average RFs, again, still below 20% here in this case. In the two problem compounds that we talked about before, the dieldrin and the endrin, we're still able to see down to 0.05 ppb or 50 ppt. Much lower than, again, most customers need to see, but what we're starting to see some from the industry is those ultra low level detection limits specifically for those compounds. Now we move into some individual compounds and take a look at those. So here is heptachlor on a 15 microliter injection and the calibration range. This is one of the compounds that tends to play a little bit nicer. We don't really have many issues with this one. So we're getting beautiful peak shape here. This is the low standard of 5 ppt. We still have a signal to noise value of almost 43. The average RF over the calibration range for the entire calibration was, again, below 8 with an RSE of 21% there. Here's the dieldrin. So again, we are still seeing 25 ppt here on a 15 microliter injection. We still have signal to noise at 4, which still meets the marks here of being above 3. The average RF, the RSD for that was 4.76 over the calibrated range, and the RSE was 5. So nice and low and very good linearity there. And here is endrin. On the 15 microliter injection, again, calibrated range of 25 ppt up to the 50 ppb mark. We're still getting great peak shape. We don't have any interferences. Signal to noise is 4 again, and the average RF is just under 7 with an RSE of just under 9 here. And again, DDT. This is still, again, the 15 microliter injection. So we're calibrated down to 10 ppt. All the way up to 25 ppb as far as linearity goes on this compound. We also did MDL studies doing both the 15 microliter injections and the 10 microliter injections. So this was the 15 microliter injections. The MLD study was done at a concentration of 10 ppt. And you can see from most of the compounds, we are below 10% as far as concentration of RSD and response goes. A couple of the ones that, again, we know have issues and do not play quite as well for the endrins and the endosulfans are all a little on the higher side, but everything is below 20% still for this. We also ran the MDL study using the 15 microliter injection at the 25 ppt concentration level as well. Again, pretty low RSDs for concentration and responses. A little bit of variability at the front end of the chromatogram on that one with the lindanes, but still everything for the most part was under 20% and correlated very well. As you can see for the conclusions of this method, all the organochlorine pesticides calibrated with an average RF of below 20. Calibration ranges were in the low PPT ranges. Again, we were able to see down to 5 PPT for most compounds and calibrate all the way up to 50 ppb, showing the linear range of the instrument. Issues of coelution and interferences, again, even the compound breakdowns for the endrins and dieldrins were solved using lower inlet starting temperatures. Being able to do a large volume injection is a good option for being able to get more sample into the system without the presence of a large solvent background. And using the MMI in the solvent vent mode enabled that large volume injection at the cool injection temperature and helped prevent the breakdown from those challenging compounds itself, proving overall that this was a very successful project. Thank you so much for taking the time to listen to the webinar here.